Hi, I'm Alan Davidson, Product Marketing Manager in the high-end FPGA team at Altera. We hope you've heard the exciting news about our new 28nm devices, the Stratix V FPGAs. One of the key innovations in the Stratix V FPGA is its transceiver architecture. With data rates up to 28 gigabits per second to address 100 gigabit Ethernet and emerging higher bandwidth applications, and backplane capability up to 12.5 gigabits per second, the Stratix V transceivers deliver the highest bandwidth you'll find in an FPGA. Today, I'm going to show you a live demonstration of Altera's 28nm transceiver technology, running a pseudo-random bit pattern at 25 gigabits per second. And we'll also look at both transmit and receive eye diagrams across a 10Gbps KR backplane running at 10 gigabits per second. So stay tuned to learn about the new technologies available for your next generation designs. Okay, this is our demonstration board, and this is the 28nm transceiver device. The output from the transceiver is connected to the oscilloscope using MMPX connectors on the board and 2.4mm high bandwidth cables. The 28nm transceiver device contains an internal data generator that sends out data with a PRBS7 pattern. Looking at the oscilloscope, you can see the transmit eye diagram corresponding to a data rate of 25 gigabits per second. Running at this rate, Altera's 28nm transceivers can drive several inches of circuit board trace for chip-to-chip and chip-to-optical module applications. While this demonstration is showing the transceiver running at 25 gigabits per second, the transceivers in Stratix V FPGAs will run at 28 gigabits per second, meeting the CEI 28G short reach specification. This performance level is ideal for 100G optical module applications that require 4 lanes at 28 gigabits per second. And the power consumption of the transceiver is very low, only 200 milliwatts per full duplex channel at 28 gigabits per second. To understand how Altera is able to achieve this performance level at 28 nanometers, let's take a closer look at the architecture of the transceivers.
When developing our 28nm transceivers, we considered many factors in device design, layout, packaging, and fabrication. For superior jitter performance of our transmitters, we use LC tank transmit PLLs that result in transmit data streams with less than 1 picosecond of random jitter. The voltage controlled oscillators in these PLLs are based on tuned LC tank circuits with integrated inductors that are created using the metal layers on the device. We introduced this LC technology at 40 nanometer with our Stratix 4 GT devices running at 11.3 gigabits per second. For our receivers, we use a hybrid clocking architecture based on analog PLLs. We first lock to the reference clock, then automatically switch over and lock to the incoming data stream. This removes the reference clock from the circuit, so there is no impact on jitter performance. Also, using analog PLL technology gives us superior jitter tolerance compared to other clocking schemes. To reduce noise, we use on-chip regulators for the critical transceiver power supplies. Keep in mind too that a key advantage of moving to higher data rates is power efficiency. Using fewer transceivers running at higher data rates is the lowest power solution. Bottom line, the combination of low transmit jitter, high receiver jitter tolerance, reduced supply noise, and lower power dissipation allows us to give you the best possible bit error ratio performance for the complete link.
Our second demo shows transmit and receive eye diagrams when driving a 10Gbps KR backplane at 10.3 gigabits per second without any external components. Here we have our demonstration board connected to a 20-inch backplane. Communication at high rates through connectors and across backplanes has to overcome frequency-dependent losses, signal crosstalk, and reflections. These effects limit both the maximum data rate and the maximum length over which the data can be transmitted. In this demonstration, we're using AirMax VS connectors and a 10G base KR backplane, both from FCI Corporation. The 28nm transceiver device is sending PRBS7 data through this connector to the backplane, then through this second connector to this SMA breakout board. The data is then sent back to the demonstration board through these coaxial cables, where it is received by the 28nm transceiver device. We have the ability to examine the receive eye inside the device immediately after the on-chip equalizer, so we can actually see the impact of the on-chip equalization. First, let's take a look at the near-end transmit eye diagram. As you can see, the transmit eye is wide open. Now let's take a look at the receive eye with the transmit pre-emphasis and the receive equalization turned off. Looking at the scope, we can see that the eye is closed and data is not being received reliably. I'm now going to turn on the transmit pre-emphasis and the receive equalization. And as you can see, the receive eye immediately opens up and data is being received reliably. To achieve error-free transmission at 10.3 gigabits per second across the backplane, you need to apply advanced signal conditioning at both the transmitter and the receiver. Here's Sriram again to explain how this signal conditioning works.
One signal conditioning technique we use at the transmitter is pre-emphasis. As high-speed signals travel across a lossy backplane, the highest frequency components in the signal see the most attenuation. Pre-emphasis amplifies the highest frequency components at the transmitter before they travel into the backplane. The idea is to compensate as closely as possible for the backplane losses. In our receivers, we have both a continuous time linear equalizer and a decision feedback equalizer, or DFE. The linear equalizer is a 4-stage equalizer that can add up to 20 dB of high frequency gain with programmable bandwidth. The linear equalizer can be programmed to a fixed setting, or it can be run in adaptive mode, where it adjusts itself automatically to changing conditions in the link. The DFE can also be programmed with fixed settings or run adaptively. The DFE uses a digital technique which in some cases can provide superior performance compared to the linear equalizer. We use a 5-tap DFE that is especially useful for mitigating the effects of crosstalk. It also works well when the backplane has nasty reflections.
Thanks again, Sriram. As you've seen in today's video, we're excited to push technology boundaries. Out of this, we hope that you'll see our new 28nm transceiver FPGAs as a solution to the bandwidth and power demands of your next generation designs. Learn more about our Stratix V FPGAs by visiting altera.com/28nm transceivers. On this page, you'll find webcasts, white papers, and more information about our 28nm transceivers. You can also start designing with Stratix V FPGAs today by downloading Quartus 2 software version 10.0. Visit altera.com/download for more information. I'm Alan Davidson, and on behalf of Sriram and the rest of my colleagues here at Altera, thanks for watching.